The main reason for doing the modal test, even if you're just extracting at your frequency and damping ratios, is so that you can validate any modeling. So you may want to just do the testing and not do any modeling. But certainly, if you're going to do any modeling of any kind, by modeling, I mean finite element analysis or other, it's usually finite element analysis. You want to validate your analysis with some sort of measure. I know many of you take an FEA as a course, finite element analysis as a course. Some of you may not have, it doesn't matter. But you certainly have done a lot of modeling in the last 4 years of your life as a student in engineering. I don't know how many times it was mentioned that you should validate any model with a measurement, which you should. So you're hearing it now. And in vibrations, you do that all the time. It's very important. If you do any modeling, you should validate it with a measurement. So that's the reason why we have a section on vibration measurement and testing. And we go over some important things. So I know you all have a course under your belt. It's called Lab 1, Mechanical Engineering Lab 1, and it's focus of that course is supposed to be sensors. Lab 2 is supposed to be about measurement. I don't know what they're really doing in there because I don't track it that closely every semester. That's what you're supposed to be doing. The next lecture or 2 or 3, we're going to talk about sensors that are used for vibration. All right, and we're going to talk about measurement for the purpose of vibration. And some of the equipment that we use, analyzers specifically that we use. We call it dynamic signal analyzers for a reason. There's a lot of similarities between those and controllers. So I lump them together when I talk about them. There's no point not talking about controllers. A lot of the basic information on about analyzers. I was talking about controllers that we use for shakers. And one of the important things, not the most important, one of the important things is the actual signal processing we do. Because vibration measurement and dynamic force measurements, which are usually go hand in hand with vibration tests, because the measurements vary with time, they're called dynamic. And we have to be very careful how we treat those in any world, but especially in the digital world. And so the signal processing becomes very important. It's kind of like a vibration isolation design. If you don't know what you're doing, you can run into problems quick. And it can be worse than just not doing it at all, sort of thing. So this is the reason we talked about this. Hopefully give you an appreciation. Whether or not you actually do any of this for a living, for your career, regardless, it's important to appreciate what's involved in actually doing that. All right, so the first point is going to be, first slide here is about vibration sensors. And make no mistake about it, for vibration measurements that really matter in a laboratory setting or an industrial setting, or for predictive maintenance, for diagnostics, we use, more often than not, in structures, we use piezoelectric accelerometers. Now, in Lab 1, we used to use one of those for the beam vibration measurement experiment, and hopefully we still do. Basically, that's a good example of the piezoelectric accelerometer. Very robust, very broad band, meaning frequency-wise, and broad in magnitude range-wise, robust sensor. Rotating equipment, we can use some accelerometers, but oftentimes we use proximity probes because they're non-contact. We can actually look at rotor or shaft displacement. And so, as you saw with the balancing kit, the balancing demo, that was what we did. Of course, here's some sketches of proximity probe, typical accelerometer, and then typical velocity sensor that we use. These used to be more common, let's say 2-3 decades ago. They're not so common anymore, but they still see them from time to time. Of course, we can sense vibration more primitively, and I don't believe we use the word primitive because not necessarily very primitive, but they're not, they're not going to quantify things like the accelerometer can. But of course, we can if you get an idea of whether or not we got a vibration change or a vibration problem, like a watch, I've certainly been able to assess a situation of using vibration problem using primitive. The other extreme, we have modern electronics that have helped having, I guess, phones, game, controls, having accelerometers. In the world of consumer or modern electronics, the word accelerometer is a little bit misused from a vibration expert perspective. Sensing G, a gravitational constant, is hardly the same as measuring or sensing acceleration from a range of a micro G to 1,000 G's amplitude, and from 1 hertz to 4,000 hertz. All right. So I'll just leave that with you, that MEMS type accelerometers that you find in consumer electronics are very limited in their ability to actually measure vibration or dynamics over any meaningful frequency range or magnitude. All right, so let's talk first about the proximity probe. We've already seen this in action in the balancing demo. It's very similar in principle to in operation to a metal detector. And of course, metal detectors have wide use. Of course, you had one as a kid or an adult. They're kind of fun at the beach or wherever you're at. But if you ride a motorcycle, you've had to experience those sensors in the road when you're trying to make a left at a light. They don't always pick up. There's usually not enough metal, or not always enough metal in the bike for the sensor to sense that you're there. And so, but the same idea, it senses the presence of metal, and furthermore, basically creates a magnetic field that's disrupted by the presence of metal. A proximity probe basically, in very simple terms, assesses that magnetic field, and the change in it gives us with some electronics, it gives us a voltage that's proportional to that gap. So if we know the gap and our prox probe is fixed, that's why we have a rigid support, mounted to a rigid support, then we have a sense of what the rotor or shaft radial displacement is. Right? So again, this is a cross section of the shaft, the rotor spinning, and prox probe. All right, velocity transducers, historically these were probably 20, 30 years ago, very common compared to the accelerometer, and widely used. They're a bit bigger, and I've got a picture of a Bentley, Nevada manufacturer. This was probably about 4 or 5 inches length and about an inch and a quarter diameter. And this is the top up here, which connects a lead or cable to, and this is the bottom here. You can see it's threaded. And a common way to mount these on a structure or a machine is to either use a stud mount, which is what we've got here, got a stud mounted to the structure, or you can use a magnetic mount. Or adhesives or waxes, like that. So by far the most common approach to use it is if they're fairly permanent stud mount, it's meant to be fairly mobile, and a magnet mount. And but anyway, if we look inside, take a slice through the middle of this thing, look at the cross section of this velocity transducer. We have a permanent magnet suspended within the case. So the outer case here, we have a permanent magnet suspended in the case, and then around the perimeter of the case on the inside, we have coil. So if you were to move, forget vibration for a minute, if you were to grab this, somehow get your fingers inside here, grab that and move that up and down, what are you doing? You got a moving magnetic field, and it's moving past a coil of wire or a conductor. What happens when you do that? Right? It produces a current. Learn that in physics, right? So that's the idea. Same principle, and if this might not have occurred to you, but same principle. Anybody into audio at all? Like if I say dynamic mic, what I'm talking about? Same principle as a dynamic mic. The only difference is instead of having a spring mount here, you actually have a diaphragm pushing on this thing. But you do have a chunk of inertia here, and that's why sometimes the dynamic mic is not as good as like a condenser mic or something like that. Same principle. If you flip it around, if you were to hit the coil with the dynamic signal of the voltage varying with time, then what would happen is you could get this to move. You could move that mass. That's the same principle as a speaker. You guys ever take a small speaker and use it as a mic? No. Same principle of operation, we're just flipping it around. In one case, it's a sensor, mic's a sensor, speaker's an actuator, but it's big, small. This is big when you have to go, but move that big. So it's a coil, basically a magnet in a coil, same principle as a speaker, or same principle as a dynamic mic. Flip it around, use it as an actuator. We use the same idea in electromagnetic shakers, which I'll show you in a minute. And we use the same idea with around anyway as the currents. All right. So if you mount this case of this velocity sensor to a vibrating machine structure, as the structure moves, this mass is going to move, and it's going to produce, because it's moving in this coil, it's going to produce a signal that we can use. And it turns out that signal is proportional to the velocity of the structure. All right, this shows what's called the frequency response, and that might be a word that scares you a little bit. Don't let it. All it means is it's the sensitivity of that sensor, that velocity sensor, as a function of frequency. So you've all taken lab 1, right? Yes. Sensors, what kind of sensors do you look at? Thermocouple, strain gauge. So you're familiar with the idea of sensitivity. What does sensitivity mean? For example, let's pick on a thermocouple. So many millivolts output per temperature change or per temperature value, correct? All right. That's it. Right? In vibrations, that's not it. In any dynamic signal, if you look at a microphone, a couple of you raise your hands if you've done with microphones, or even if you've done things with speakers, actuators and sensors that are subjected to a dynamic environment. And believe me, like audio is a dynamic environment, very similar to vibrations. It's important what the sensitivity is as a function of time, or as a function of frequency. All right? So this is a velocity sensor, frequency response, but it could very well be a frequency response for dynamic height. All right? What can you tell me about that frequency response that would be desirable for a dynamic light or a velocity transmission? Yeah, specifically. All right. Why? It only goes up to 1500 hertz. But if you had to, like, say something, let's say this. And that. Why is it good? All right, I'm looking for a specific word here, or a specific comment. Why is it good? What can you tell me about the sensitivity as a function of frequency? Why? All right. In other words, if you're singing bass You're singing soprano. It's treating you guys the same, right? Same sensitivity, right? If there was a peak around 1,000 hertz, all we hear is a soprano, all right? You know what I'm saying? That's the sensitivity much greater for the soprano, all right? So for measurement purposes, we want a flat frequency response. If you're into audio, if you ever get into audio, and I don't mean just mics, I mean just a good sound system, you want a flat frequency response. You want your speakers as a group, usually because they're the little ones, you want it to be fairly flat. So usually a good, subs take care of the low end, and there's a crossover. You cut off everything where that speaker doesn't try to stop, and then there's a high. So the end result is that you have a fairly flat frequency response. And so the idea of having flat frequency response for both sensors and actuators, like mics and speakers, for example, is what? You actually hear what it's supposed to sound like. All right? So how many of you listen to like really old music? Anybody ever? How old? What? Like old blues or jazz. So if you've ever done that, you like notice that it's just something just not, you can tell it's old. It's not that they all sang it, because the stuff that we recorded them with wasn't that flat. It had a very certain frequency. In fact, you can go in and modify audio so that it sounds like it's old by just applying a frequency response that would be the same effect they had recorded it with the mic. All right. I used to do a lot of old blues. So, all right. So this is what we call a frequency response. If you ever, buy a mic or speaker or an amplifier for audio purposes, or if you get into vibrations or any kind of dynamic measurements. Dynamic measurements or actuation. Control is another area. Very important. You want to understand what your sensitivity is as a function of frequency. It tells you a lot. In other words, in this case, it tells us basically 8 hertz and 1,500 hertz is pretty flat. So as long as we're measuring in that range, sensitivity is flat. What if you got it like, or maybe your vibration component, or the only vibration component at 5,000 hertz? This isn't going to be a very good sensor. I don't know. I see it, I hear it, but I can't measure it. All right? Or if you have a soprano at 2,000 hertz, we're not going to hear it. All we're going to hear is live. All right? So it's called frequency response, basically sensitivity. Any dynamic sensor that you buy or look at, or any dynamic actuator that you buy or look at, whether it's for audio purposes or for engineering purposes, vibration purposes, this is going to be one of the things that's in the edge section. It's not in my own way. All right. So that's all I have to say about that. The accelerometer is by far the most commonly used vibration sensor for measurement purposes in industry and in that type of field or not. This is an image of one made by USF at New York, similar to the one that you should have seen one, right? All right, if you put it in perspective, it's about, I think it's like half an inch, quarters of an inch in diameter by a couple of things about it. The point where we connect the cable, there's a couple different ways to do it, but for a smaller accelerometer like this, they use, it's a coaxial cable that will connect to it, but it's, this particular one's called a micro dot coax connector. Micro dot coax connector. And the thread on there is 1032. Just like here, how many of you know what 1032 means? How many don't? You really should get a machinery handbook, or go back to your machine design book and look at the chapter on fasteners, study fasteners. All right? 10 indicates the screw size, 32 indicates how many threads per inch. All right? But as mechanical engineers, we should all know, basics about fasteners. Usually a step down, if you're actually buying bolts or screws, it's a step down from a quarter 20 or quarter 28 would be quarters of fine thread for quarter%. So it's not a bolt, we don't use it as a bolt, it's a standard connection that we use for smaller components. We want to have a coaxial. We have a housing on it, and the bottom of the housing has like a hex shape to it. The reason why we put a hex shape, manufacturer puts a hex shape here is for custom things. Sometimes we glue these guys down to the structure of machine measure. And the best way to remove them is to apply or shear that. The best way to shear the glue bond is to actually put a small wrench on there. Whereas you can't see it, it's usually a back hole, thread hole. And you can stud mount these into the structure, more permanent installation. You can also attach these things with wax, which is what you do in lab 1. And then there's also magnet mounts, other mounts, thread in, and attachment. This is the caution section of the thing. Let's start at the bottom. We've got our vibrating surface at the bottom. We're stud mounted. In this case, we use an isolating washer. And I'll just make a comment on it because I have a fair amount of personal experience with this. You take a vibration measurement on something that has a large potential for static charge. And I did some work in the years on high voltage circuit breakers and transformers. Well, I could put these things out in the breaker and you draw in hard from 6 inches away. Anyway, so we put a ceramic washer in there. Why would you use ceramic? It's not good, that's the most important thing. Well, it's good for compression. Yeah. So it's good for compression. You wouldn't want to put anything soft in it, right? Why would so like something like CA glue, CA adhesive? That's ideal because it's so thin and hard when it cures that when it dries, that it's almost like it's not there. Wax, like wax works. Usually when you apply it, I don't know if you're touching that one, a little bit of wax on there. Beeswax is what I use. I'm not sure if you guys use that wax, but I use beeswax and I'll use that when I do the structures. You put a little bit on there, warm it up with your fingertips, and then apply it, push, and turn. And it squeezes it out. And not as good as like stud mount or CA glue, but it's reasonably good. What happens is if you get something that's too soft in your elastic, you change the frequency response to the sensitivity of this all-around. Right? So you want to keep this as possible. I think one of the homework activities is for you to go to PCB. I give you a link, I don't want to go into it, but basically go to the PCB website in New York, which is outside of Buffalo, and just take a look at the different mounting options. They'll cover all the ones that I just mentioned. All right, so the classic question that I like to ask them, that's was 3 or 4 ways to mount an accelerometer. Doesn't mount, glue, and pop, if you like, wax. And people get creative. Screw, fastener. Those are probably good stuff. Okay. All right. So here's a cross section of the accelerometer, and so we have the case. The bottom of the case here actually is solid. But up in this area, we'll have the main part of the accelerometer. And right in this area here, this shaded area is called the mass. But it's really called the seismic mass. In this solid mass. Below this mass, we have a stack of thin slices of quartz crystal. All right, anybody like rocks? Yes. Okay. Good. All right, you of course. Did you discover anything clever with quartz? Anything else? All right. That was good. These are all good observations of what you.
I mean, I'm good.
All right. So my kid did when he was reflected like everything. All right. So, but at one point, and he said they're smacking them together. Of course, it's lighting up because of these electric. So quartz crystals and other crystals, but quartz in particular, when you apply, when you form them, they basically generate a charge. Don't get too excited. You're not going to save the world's energy crisis. Pico Coulomb. Okay, you guys remember Pico? Well, I see you guys all the time. He's really good with that. I see folks where you know, piezoelectric sheets or whatever in your sleeve generate power to charge your phone. I mean, seriously, it's like using an accelerometer to charge your phone. Good luck with that. You got a lot of time. You really are running hard. So piezoelectric crystals are used for load cells. In fact, in that case, you just sandwich them in. And I've got those. I'll show you when I talk about impact in a minute. You deflect them, and they produce charge proportional to the deflection, which are also very elastic and linear. So that deflection is proportional to what? They're elastic and linear. So that deflection of something that's elastic and linear will be proportional to what? Force. So they're great for measuring dynamic force. Now they're not good for static force. Guys, they should know better than math to do this. So we use them to measure the preload in a joint. These electric are great for dynamic. They're great for picking up a change in force. If you take it, put it on the end of a hammer, smack something, it's going to go from 0 to whatever your force is, maybe 1,000 pounds, like 100 pounds. How strong you are, how hard you hit it. And it'll record that. If you sit there and just screw a bolt and nut down on it, it'll go up to 1,000 pounds, and then it'll just dissipate all on its own. All right, so they're not good for static forces. They're good for dynamic. In this case, we're not using force, so we are, which is inertia force with mass. We're sandwiching it between the seismic mass and the case bottom. And there's two ways of attaching it. One is glue, the other is to actually use a bolt. All right, some sort of fastener, and bolt it right down. All right, to the bottom of the case. Either way, it doesn't matter which way you do it. Both ways. This is a little bit more secure. If you use both, they're usually going to be very shock. If you don't, they're not. And then if you get to the hands of the wrong person and you drop, then you create like $1,000 raffle. So in any event, what happens is when your machine surface that this is attached to the case moves, because the seismic mass inside here has inertia, it's going to move, it's going to generate deflection, which is going to generate with a charge, picocoulomb level, and we can measure that charge. 30, 40 years ago, we did measure it. You could have accelerometer, and there'd be so many picocoulombs per G of acceleration. You'd have a very short cable. Charge amplifier, we could take that picocoulomb signal and shut all the lights off before we wanted to affect the signal. And then you could that signal conditioner, starting amplifier would bounce it up to 2 millivolts signal that you can look at, analyze, or whatever. PCB is the company that led the way and actually introduced some internal electronics, which are fed through cable, powered like panel power, like that's not exactly the same idea. The power with cable, and the conversion from picocoulomb to millivolts is taken care of internally. All right. So now they want to get a charge. So they're all that little electronics. Again, let's try to just show you what we want to do. So there's some internal electronics that takes care of that conversion. In your lab one experience with accelerometers, you had an accelerometer on a beam cable to a small blue box. That small blue box basically provided the power to the electronics. You guys remember that? And there's a cable from that box. The analyzers that I use, almost every analyzer that I have, has the built-in capability of providing the power to the accelerometer or motion. All right, so if we were to look at the frequency response of this, so the output of this is millivolts per G. We look at the frequency response of this. This is what it looks like. I guess we go back to that previous picture. You have solid structure on the bottom. Bottom of the case is like a chunk of metal. Then you have a stack, absorbable for a minute. Crystal stack, which I said, I don't know what it is, fairly thin, and it's linear, and it's elastic. Then we have a small mat. If you have a model of that, just real quick, what would you use? That's spring, right on. That's spring. It's actually a really good example application of a simple mass spring system. But M is usually pretty small, very small. K is usually very high. So where's that put your natural frequency? Spring K over M, pretty high. All right? Pretty high. That's exactly what happens here. So this is kind of a weird sketch. But you have an actual frequency from that stiffness of this crystal, and you have and from the small size of mass. But there's a range where it's flat. Again, this is your sensitivity. This is how much output in millivolts you can get per G of input. Right, so no matter what the numbers are, this ratio is what's important for our sensitivity. How many millivolts you get out for how many G's of input? In this case, it's 100 millivolts, which is kind of a typical number. There's a whole range. All right, so this is kind of typical for structure. Wherever this is flat, and you call it linear, I guess I just call it flat. That's where the sensitivity is saying. $2 frequency. So if you have a frequency here, the frequency here in your structure or your machine, your sensitivity is going to be the same. So you're going to get a measurement that's representative of what's happening in the structure. Now, I don't want to give you the idea that this is not a broad range. This is kind of an older plot. The newer designs have pushed this down a factor of 10. So you're down closer to half a hertz, so good for it's flat, and get them to go up to 4,000 or 5,000 hertz. All right, most of the ones that I have, I'm usually interested in measuring up to 50,000 hertz. Go up to that range down to a couple hertz. All right, it's flat. Any questions? Yes.
So, I mean, I didn't talk about 50% where you have your range for that area.
Yeah, you're well within this range. Yeah.
Is there any time it's like, you can do like, like, essentially this, to measure that range
Absolutely. Do what we shake yourself down. So the question is, what if this is all we got? We got the really, let's say 250 hertz. Those are magnets very. This is our sensitivity. If you put this on a machine and you happen to have a vibration here, it's all you're going to see, probably overload. Right? Overload. Now, if there's any other vibration that's happening, you're not even going to see it because it's not. So your question is there a way to still somehow use this? I don't know of anybody that does it. Around if you were to multiply this by the inverse of this response, then you should get something flat. Now, the problem with that is if there's any change, then you might not get it. So we use it to drive shakers all the time. Use dynamic flow with infrared. All right, so knowing the frequency response, and you could always multiply it by the inverse of the response. All right, folks do that in audio all the time. We call it EQ.
So, yeah, also, question, those velocity kind of getting smaller?
Yeah, those are pretty big. The ones that I have a few, and I think the smallest I've seen is like 2-3 inches high.
There's no kind of reason to use them over.
No, and I've never. I mean, I've got them just because they're either give it to me or I inherited them or something. I didn't buy them, but some numbers I bought. So the other, so two very important things. This is just like, I don't know, bashful or don't want to ask questions. So this last test that is coming up at the end of the semester, there's going to be questions, not problems. One of the questions that I know I've asked, right, almost everyone who's tried so far, have been possible questions. Like, so for example, say, guess the frequency response of an accelerometer, you know, I like the main points. What are the main points? That. You call this the useful range, the flat range, the linear range, because that's what it's in your notes. We call it flat range. And then, you call it amplitude, but only sensitivity versus frequency. All right? This is a very important number. This is our sensitivity. And again, like I said before, when you were pushing into the sensors, you just got one number. You didn't really even think about frequency, most likely. When you start looking at sensors or even actuators that are used for dynamic purposes, then this becomes something that you want to look at as a function of frequency. You want to make sure you understand what it is over the range of frequencies you're going to use it. If it's flat, great. If it's not, then you might need to find a way to compensate. All right. This is actually the sensitivity that we're seeing. And usually, if you just see this on a spec sheet, there should be some sort of plot like this as well. But even without the plot, they'll give you the sensitivity, and then they'll indicate a frequency range. In this case, they might say from 5 to probably like 2,000 hertz or something like that. You know, plus or minus 1 millivolt per G or something, whatever it is, power. All right, so just one final thing. So that frequency range is not the only thing important. The other thing that's important is the magnitude of the sensitivity. And so, for example, I've got some that are measuring micro G levels. So the sensitivity would be like 10 micro G per volt. That's not something you want to put on a machine. It's something you want to put on something that has very little vibration, very low level vibration. For type of equipment that you or, and then going the other way, you have some accelerometers that are really all shock accelerometers designed for picking up vibration, acceleration, the environment for shock. So in that case, so in that case, the sensitivity is a lot lower. Higher. So this is the reason why I prefer accelerometers, general purpose. The Fox probes certainly are best for rotors in my mind. I like them to give you an idea what your actual displacements are with the rotor. They go right down to DC. In other words, if the rotor's not moving, you can still measure the gap. Velocity sensors are a little bit more limited. Accelerometers, much broader range of relative. All right, so those are sensors. The next thing I want to talk about is ways of introducing vibration. So, a lot of equipment creates their own vibration problems. Right? So if you've got a machine that's got rotating or rotating motion, or parts that integrate their own vibration problems all on their own, you don't need to cause them. But there are plenty of cases where we want to study the dynamics of the structure, determining acupressure, bone shape, and so forth. And you therefore need to cause the vibration. So we call these vibration exciters. All right, they fall into two different categories. Again, this is like a typical question I'll ask. Those are two possible types of vibration exciters, shakers, and hammers. Right? And within there, what are the possible types of shakers? We have hydraulic, electromagnetic. Electromagnetic by far is the most common. Piezoelectric, we actually put the idea of the accelerometer around instead of measuring, basically apply a charge, dynamic charge, and cause vibration. And then mechanical. We've all seen the mechanical if you've ever bought paint. Of course, they make big boy versions of those cars or anything else that you can imagine. Mechanical, I guess, there's different ways of causing vibration mechanically. Any sort of actually rotating and balance. Buzzer in your phone, the buzzer will be waiting in line at the restaurant. Those sorts of things. But if you scale that up, you can call it vibration. Again, by far, electromagnetic is the most common. That's the one to look at. Most of these are electromagnetic shakers. And then hammers, really the only type of hammer that I'm aware of that's used for vibration. You're actually sensing what you're applying is a piezoelectric. Use any hammer you want, but that's force So this is a little bit smaller than a carpenter hammer. I'm bringing these flaps, and this is the ENC coax connector looks like. Use the oscilloscope in lab 1. That connector is coax. It's about 8 inch diameter right there. And then I've got some little hammers. These are real small hammers. That's another microdot or something. And these are more the size of a small pencil. And then we've got smaller hammers. Right? One of the things that you get with a hammer is a tip. This is the rubber tip. There's a metal tip, plastic tip. They screw on the end. Right next in line is your piezoelectric force sensor. And that looks like the accelerometer, just a stack. There's no mass inside there. You're just squeezing a stack. And then the rest is built electronic wiring. All right, so let's talk about shakers. Electromagnetic shakers are one we're going to talk about. There's a couple of things. There's basically 3 points that I want to make. One is the middle point here. There's different ways we can connect shakers to structures or structures to shakers. So if you have a smaller shaker, and I picked a structure like just a cantilever beam or structure, fixed at one end, free at the other. And if we want to drive that with a shaker of some force at some point, we can grab a smaller shaker and place it near the structure and then drive it with a force transducer on the structure. Now, one of the problems with connecting, so electromagnetic shaker is the same idea as a speaker. Can still make speakers. Okay, Anybody ever do that? You did? All right. So the idea is electromagnetic speaker, an audio speaker is basically just a coil in a magnetic field, right? And how do we get that coil to connect? Coils attached to a cone, plastic. All right. Then you get a low-level signal, which nowadays, I guess your low-level signals are all coming from your phone, right? Some low-level signal. You hook your phone directly to a good speaker, right? Why wouldn't you do that? Why would you not connect your phone audio output directly to a good speaker? Because that speaker can pull some current, right? So you want to basically, you need a power amplifier. The power amplifier takes a low-level signal from your phone or whatever source, low-level signal, photograph or whatever, takes that low-level signal, hopefully doesn't modify it because its frequency response is flat over the range of frequencies that you're going to be listening to music, and then it provides a significant signal output that looks exactly like input except higher voltage and more current capacity, which means the speaker, the activator, can pull a lot more current from that without science propagation. So shaker is the same idea as an audio speaker, but instead of having a converted plastic tone, it has a linear armature. All right. So it's basically the coil has usually a plate and with these don't really show it that well here. So inside these things is basically a coil and an armature, and you connect a signal to this that basically comes from a power amp, and it'll bump up whatever you're putting into it. So with shakers, so let's tell you an example. You start with a signal generator, which could be a simple function generator that produces a sine wave or a random signal or a swap sign. Put that into a power amp. Power amp then is connected to the shaker. It drives it with whatever the signal generator is. All right, more sophisticated systems, we put this accelerometer on the armature of the shaker. Feed that back into the signal generator. The signal generator is really a controller. You look at the signal it's sending, you look at the signal that it's measuring, compare the two, they don't match. That's the vibration. All right, so there's a couple ways of attaching these things. One is direct. That's the one that I'm showing at the top here. The one at the top is through a stinger. In this case, we have a structure in its whatever location that we bring the shaker to it, and we want to apply a force to it, and so we want to connect it. And if we were to connect the shaker directly to the structure, it would be very hard to control the direction of the force. See that? So what we do to help control the direction of the force, we introduce a long, slender, but stiff structure called the stinger. And so basically, if I take like a long stick, if I take a long stick, like a rod, metal rod, and push it on you, which direction the force is, it's only to come straight at you, the axis. Whereas if I were to, anyway. So the idea is that this controls, the purpose of the stinger is to control the direction of the force. And there's another thing as well. Controls the direction of the force. The other thing is the shaker armature consists of the coil and any sort of mounting plates and so forth. What do those things have? They have mass. All right? If we were to attach the armature of the shaker directly to the structure, what would we be changing? The mass. We'd be changing the mass. We'd be changing the natural frequencies, the load shapes, and everything else. So by introducing a stinger like this, we reduce that effect. That effect is called mass loading. So if we were to attach the shaker right up here, we'd be mass loading. If you apply a force, you'd be adding mass. You don't know what you have. So introducing a stinger does two things. What are they? Control check. Corrects the force, reduces mass loading. Right? Everybody got that? Reduce mass loading. Does that make sense to you? All right, so that's the other approach is direct. In that case, you have a big shaky table. This one's turned on an axis and it's got a table that's moving back and forth, but it doesn't have to be. You can push it up and down. You connect your structures or your equipment, electronic equipment has to go through shaker test. Anything you attach it directly to the shaker, and then you drive the shaker or whatever vibration required. That's what we mean by connection. Two different ways: direct connection and then through a stinger. So when it's a direct connection, you're providing the vibration environment. Usually with a stinger connection, you're applying the dynamic force. All right. Let's talk about signal input. So, like, you don't probably even think about the signal input going into your speakers, your audio speakers. It could be anything, right? You could play sine waves if you wanted, right? But you really don't like listen to that probably. But you could. If you did that, it's called a sine wave. Right? So you could drive the structure, you could drive the shaker, or whatever's attached to it, at just one frequency at one magnet at a certain level. So you could say, okay, we want to drive it at this frequency, let's say 500 hertz at 10 Gs. Right? 1 G is, we use G as a unit for acceleration. Or you could say, I want to drive it at that frequency with peak to peak amplitude of a tenth of an inch, or a velocity, or specify whatever you want. Specifications for different tests, vibration tests, do exactly that. You may have what's called a sine wave. We also have, and this is for the purposes of determining the frequency response, we have what's called a swept sine. In this case, we start at a low frequency and sweep up. All right? In fact, if you think about it, I only showed you frequency response for sensors here, but I could have showed you frequency response for structure. This is exactly how it's converted. You apply a known input at a certain frequency and sweep up. As long as your input is flat, your response will give you your frequency response. We'll show you how your output is changing with respect to the input. So that's the other type of input. Obviously, we can hit a sine wave or a swept sine. Swept sine is very useful for purposes of determining frequency response, because then you can see how this responds over a range of frequencies. So, for example, if you're sitting there driving, see, we attach like this guy right here. This structure right here, we're driving in from very low frequency to very high frequency, and we get a lot of response at, let's say, 300 hertz. What does that mean? We have the actual frequency measure. All right. So you can sweep up or down. You can adjust the rate of which you sweep. Another type of input is a random input, random signal input. And in this case, and this is maybe something you've never thought about, but you can actually, if you look at the frequency content of a random signal, what do you get? Very good. Yeah, so you can represent a random signal theoretically with lunchtime. If you were to take, so we can quantify with this random signal. Random signal is what we usually consider broadband. It doesn't have to be real broad, but it generally contains more than one frequency. An ideal random signal is called white noise. You've heard of white noise. How many know what white noise is? What is it? All frequencies are represented. All right. So if you look at the frequency content, and I'll just draw it because I want to ask this on a test too. What's draw the frequency representation of white noise. You got some white noise signal from a signal generator coming out of the speaker or whatever. Here's frequency, hertz rate, whatever. And here's your amplitude. That's white noise. Flat. Right? What's it sound like? A little more bass. All right? It's just flat. Everything represents. Is this possible? Only on paper, in our minds. All right? What's realistic, though? Well, what is realistic is broadband. So you can use a random signal to maybe, on average, give something like that. So a low frequency, high frequency. And a vibration shaper controller can help us specify with the vibration shaper controller. And we want to set at this level between these frequencies this amount. And of course, you can be flat, you can be forward, you can do whatever you want. Specify the work. All right, so those are the three different types of signal input that we usually have. All right, next thing I want to talk about is hammers. If you look at a hammer hit, it's going to produce a force. You look at that as a function of time. Here's the force of the hammer as a function of time. An impulse. So it's 0, and every time you hit, you get that. Okay? Let's say that's done with a steel tip hammer. Let's say I hit the steel tip off, now I put a rubber tip on the hammer. What's the same energy put in, but the force is reduced and the duration is greater. All right? If you were to look at the frequency content of this is something we might not talk about. If you look at the frequency content of this, the same force as a function of frequency. What we find is this. Let's pick on that steel tip first. First pulse. It's actually going to excite a fairly broad range of frequencies. Evenly. All right? And then fall off. The rubber tip, that's steel. I'll put acid on it. The rubber tip is going to do the same thing, but not over a broad range. All right? So, I'm sure we've all done this, right? You strike a piece of metal with another piece of metal, what do you hear? All right. Hit it with your knuckles with a rubber hammer, what do you hear? You don't hear any more whack. You're not excited, let's hire. All right. So we use this for quick, I don't say quick and dirty, but we use this for quick tests. They're a lot easier to kick. It's take a long time. Take a long time. Wherever you have mounting fixtures and so forth, or whatever you're testing. Table hammer, you just show up, start smashing stuff. Right? And so the only thing you're going to be concerned about is what frequency range are you trying